In this lecture, we'll be talking about some special matrices, and they are very natural. So keep in mind that how did we get into matrices? We start first with the linear system. From there, we got the coefficient matrix as being a two-dimensional data entry. And after 1800, we started to study matrices by themselves. Okay, so now a standalone object. So matrices as an independent object. Okay, so for example, just in order for us to talk about these special matrices, let us go to when we did the linear system. So let's consider the linear system A times X equals B. And I'm assuming that A is square matrix for the sake of argument, just for the sake of argument. So the row elementary operations allowed us to find an equivalent system which has the form Tx equal C. And the matrix T, what we call the row echelon form of A. So T is the row echelon form of A. So it has a special form. So if A is matrix, square matrix with size n, so A, then T is also square n. So if A is square of size n, then T is also square of size n. What's interesting about T, and you'll understand in a second why we call it T, is that it has this form. Okay? Okay? So the elements under the diagonal are all less than, I'm sorry, they are all equal to 0. And so this matrix allows, as we said, for solving the systems going from the bottom part up to the first unknown. We start with the last unknown and we come back to the first unknown. Of course, we can do the reduced echelon form, which makes it even better. But for the time being, it's just I want to focus on some special types. So what are these special types? So we start with triangular matrices. Triangular matrices. So triangular matrices are of two types. So you take a square matrix and you look at the diagonal. Okay? So either you have the zeros below and all the entries are above it. So we say upper triangular. Okay? Or we take T equal, the elements are again, but the zeros are above the diagonal, the main diagonal. So in this case, we say lower triangular. It's just a terminology. Okay? So as we said before, when you take a square matrix for a linear system and do the row elementary operations, we end up into an equivalent linear system where the coefficient matrix is now upper triangular. Upper triangular. So what happened if a matrix is upper and lower? So here, if T is upper and lower triangular, then what happened? Then above and below the diagonal, you have zeros. The diagonal, all entries are zeros. All entries are 0. So what you have basically is something of this form, 0, 0, and you have some entries on the diagonal. So we call it a diagonal matrix. So this is known as the diagonal matrix. Diagonal matrix. So keep in mind that a diagonal matrix, we can put the numbers, because there are only n entries on the main diagonal, so we call them D1, 0, D2, 0, etc. till the last one, Dn. Okay, so D1, D2, Dn are the element of the diagonal, okay, of this matrix, and diagonal matrix. Now, the diagonal matrices are quite interesting. So for example, if you take the product of two diagonal matrices, so let's call it D and D star. So if D star is equal to D1 star, D2 star, sorry, Dn star, diagonal, huh? Then D star is in fact diagonal. It's not very hard to do, and what we have is D1 star, Dn star, 0, 0. So we multiply only the element of the diagonal, okay? And this really is interesting. Why? Because this will allow for easy computations, very, very crucial computations of the powers of D. Okay, so D squared will be D1 squared, Dn squared, okay, D cubed will be D1 cubed, Dn cubed, etc., etc. So we can easily take all the powers by taking the powers of the element on the diagonal. So this is extremely important. Okay, yeah, we will see later on if we are able to take a square matrix and somehow reduce it to a diagonal matrix, what we call the diagonalization technique, then we can compute easily the powers of that matrix. Okay, it's not clear how to compute the powers of any metric, but for some special matrices, yeah, we do. And the reason is because we know how to compute what? The powers of a diagonal matrix. Okay? How can we generate a diagonal with this? So here, a remark. How can we generate a diagonal matrix from a triangular matrix, whether it's upper or lower? So what we are going to do, let's take for the sake of argument, just for the sake of argument, let T be upper, triangular. Okay, then T can be written as we put in, okay, so it's like this, huh? So we have some entries, zeros, and all the entries are above what? The main diagonal. So what we'll do, we will split this T into two parts. So we start with all the elements on the diagonal plus, and we take 0, 0, zeros, and all the numbers above the main diagonal are the same entries as T. Okay, so here T is then equal to D, the diagonal matrix, plus this matrix J. J is just for a great mathematician who worked on matrices, and did some amazing discoveries about the structure of the matrices. His name is Jordan. Okay. Anyway, so what's amazing about J, and you have a similar one where all the entries are below the diagonal, so it is a triangle. So J, the Jordan matrices are triangular matrices with zeros on the diagonal. That's what they are. Okay. So what is special about them? It's really interesting here. Okay. So be very careful. I will never claim that D and J, they have some nice behavior. Okay. In other words, they commute and so on and so forth. I don't know that. But what is special about J is the following. So let me give it to you as an example first, and you will understand. So let us take J equal the matrix no, let's take T. Let's start with T. So set T equal, okay, 1, 0, 0, 2 minus 1, 0, and 1 minus 3, 2. Okay? So what is D and what is T? So easy. D are the element of the diagonal. So this is equal to D plus J with D is equal to 1, 0, 0, 0 minus 1, 0, and 0, 0, 2. Okay? And J is equal to 0, 0, 0, 0, 0, 0, and we have 2, 1, and minus 3. Okay? So what is special about J? So J squared, okay, equal to 0, 0, 0, 2, 0, 0, 1 minus 3, 0, time 2, 0, 0, 2, 0, 0, 1 minus 3, 0, equal. So, because the first column is 0, 0, 0, so we have what? 0, 0, 0. Yeah? Second column, 2, 0, 0, so we get what? 2 times zeros, 0, 0, 0. Okay? And 1 minus 3, 0. So when you multiply the third column with the first row, you will get minus 6. Okay? And after that, you will get 0, 0. Okay? So it's really interesting how if you take a line parallel to the diagonal, in J, above the diagonal, you have these two numbers, 2 and 3. It's right here. Let me put it. So this is the line above the... This is the line above the diagonal. Okay? But once you took the square, it pushed the line here. Okay? And below that line, all of the entries are 0. Okay? All of the entries. So what happened when we go to J cubed? So when we go to J cubed, okay, the line now escaped, that number minus 6 gives me 0, 0, 0. Okay, so after J cube, the cubed, you get what? 0, 0. And that's exactly the same, for example, here. Let me give you another example. So if we take J equal 1 minus, 0, 0, 0, 0, and 1, 0, 0, 0, 2, 0, 0, 0, minus 1, and 1, 2, 3, and 0. So if we take a 4 by 4 square matrix, which is a Jordan matrix, then if you look at here, this is the line above the diagonal, and that's what defines J. So when you take J squared, that line will be pushed up. So you will have 0 on the main diagonal, and the next one it will have 0 and some entries here. When you take j cubed, it will push to one more. Zeros, 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 and you have one number here. And if you push to j4, that number leaves and we only have zeros. So in fact, what's interesting is that about these matrices, so if you take any matrix J with size n by n, then, and by the way, it doesn't have to be upper, it can be lower as well. So j to the power n is the 0 matrix. So you see, we only have to worry about what? j1, j2, all the way to jn minus 1. After that, you are all the powers are equal to 0. So next, we want just some basic properties before I close this note. Some basic properties. Okay, so what is the transpose of an upper? So obviously, if you take triangular upper and you do transpose, you end up having lower triangular. Okay, and vice versa. The transpose of triangular lower matrix will give you triangular upper matrix. Next, what if I take T upper times T upper? The product of two triangular upper matrices, you will end up into an upper triangular matrix. It's just computations, okay, with the general formula for the product. 3, what happened to lower? Same. T lower will give me T lower. Either you do it by hand or you can use the transpose, the properties of the transpose to get it, okay? So this one is a little bit tricky, so let me put it separate, okay? So let's make some comment and then explain this one. So what did we say about, let's say, a remark? Let's put it as a remark here. So we said, if A defines a linear system or the linear system, A times X equals B. B is the non-homogeneous term, okay? And then what did we do is that we did the row elementary operations. And we end up into something like Tx equals C, where T is upper triangular, okay? And what's interesting is, what happens if we do now we continue with the row elementary operations to get the reduced echelon form, row echelon form. And we said that the reduced form will be I if and only if A is invertible. Okay, so it's the same because they are all equivalent. So T is invertible if and only if the reduced row echelon form, the reduced row echelon form will be IN. So if we are able to go up and there are no non-zero rows, then we are okay. Remember that one way in order for us to get the IN, the leading coefficients, they must be equal to 1. So if they are not equal to 1, we divide by these numbers, okay? Which tells us, in fact, it's not very hard to see that in this case, T cannot have a zero in the diagonal. So T has no zeros in the diagonal. Okay, in the main diagonal. Okay, so a coefficient matrix, I'm sorry, a square matrix, which is upper or lower triangular matrix, okay, will be invertible if and only if there are no zeros in the diagonal. And the reason is because we said that we want to have from the row elementary operations, we want to end up into in as your reduced row echelon form. Okay. Next, I want to talk about another object, okay, and we will conclude with that, is the concept of symmetric matrices. What is known as symmetric matrices. They play a major role, and we will see them later on when we do Hilbert spaces and the cross product, etc. They are very, very interesting set of matrices. Keep in mind how, as I said at the beginning, to go back to what I said at the beginning, how did we come up with a matrix? Okay, historically I'm talking about, from a linear system. Naturally, a linear system gave me a set of two data entries that we call the coefficient matrix. Okay, and once this object was born and people dealt with it, and those all row elementary operations, Gaussian elimination, and so on and so forth, we end up into what? These objects that around 1800 people start to study by itself. So not connected to linear system. Okay? So this class of matrices is very important. So in order for us to understand this, so the definition first. So A is symmetric. It's just if and only if A transpose is A. Okay, example. It may sound like dry definition. If we take 1 minus 2 minus 2, 0, and we take the transpose, we will find 1 minus 2 minus 2, 0, because we are reflecting along what? Along the diagonal, and the numbers are the same. So this is an example of this, okay? And I mean, I'll leave it to you to come up with any size you want, okay? So let me show you something interesting, how to generate some symmetric matrices, okay? So let's take a non-symmetric, huh? So we take, for example, 1, 0, 2, 3, okay? And we know that A transpose will be 1, 2, 0, 3. So what is A transpose? A transpose. So this will give me 1, 0, 2, 3 times 1, 2, 0, 3. And this gives me what? 1, 2, 1, 2, that's 5. 1, 2 times this, that's 6. 0 times this, 6. 0 times this, 9. So it's interesting that the end result is symmetric. Okay, and what's amazing is that this result has nothing to do with this example. In fact, we have this beautiful result that says that for any matrix, square matrix A, the matrix A transpose is symmetric. Okay, and you can take, for example, the proof of this is that, for example, Y is not really complicated. If you take A transpose and you take the transpose, okay, so you will end up, remember how it switches the matrices, huh? So it's A transpose time A transpose, huh? Okay, interesting. And A transpose is A, so this will give me A times A transpose, and that's exactly what we said. So let's say, for example, remark. What happened to the product of two symmetric matrices A and B. Okay, both of them are symmetric, and we're looking at the product. Will we get a symmetric matrix? So let's find out. We have A times B, and let's take the transpose. Okay, so this will give me what? Will give me A. I'm sorry, not A, because remember, this is the fundamental property of the transpose is B transpose A transpose. But we said that A and B are both symmetric, so this gives me B times A. So when do we have AB symmetric? Okay, so this will happen if and only if, in other words, AB transpose will give me AB equal to BA. So this AB is symmetric if and only if AB is equal to what? To BA. In other words, they commute. Okay, they commute. Finally, what happens if a matrix is symmetric and invertible? Okay, so here, result. Okay, so if A is symmetric and invertible, then what do we know about the relationship between what is the transpose of A inverse? We have seen that this is A inverse, I'm sorry, A transpose inverse. So, okay, so the transpose of the inverse of A is exactly the inverse of the A transpose. So if A is symmetric, this will become what? A inverse, because A transpose is A. And therefore, A inverse is symmetric. So if a matrix is symmetric and invertible, its inverse is also symmetric. There is a lot more to say about matrices. I mean, I don't mean that this little introduction to some special matrices will be enough to describe all of them, by no means. But it gives us a feeling of some basic special matrices that we can work with.